Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 11 of a unit current electricity. In today's session we are going to discuss about the Weston's bridge first and then we will switch to the potentiometer. So let's begin with the Weston's bridge. Yes, actually we have done the applications of the Weston bridge and capacitors as well as in the series and parallel combinations of the resistors. Here we are going to derive it, and let's check how we assume that the current from the fifth resistance is 0. So let's have a look. What Weston bridge is? We say it's a Weston bridge is used to find out the unknown resistance. It is used to find out the unknown resistance in a given network. On which principle it uses that current does not flow between equipotential point. When we say equipotential, we say that potentials of this point will be same. That is what we understood by the equipotential. That potential of those points should be same. That point can be considered as equipotential point. So let's look at here. That let's suppose a circuit has been given and we have four resistance. They are the R1, R2, R3, R4, and here one of the resistance would be connected and even the galvanometer is connected. I hope you understand what galvanometer is meant for. What does it, why do we kept galvanometer over here? What is the use of it? We can say that galvanometer is used to sense presence or absence of electric current. It is there to feel that whether current is going or not, current is flowing through this path or not. That can be measured by the galvanometer. Yes, so let's suppose a current I is living from here, and when it reaches here it would be having a two parts. One would be the I1, another would be the I2. It is I1 is moving from here, I2 is moving from here, and from here one more current is flowing, that is the IG, that is the current through galvanometer. And as IG would be here, I2 is moving from here. So at this point, at junction D, the input currents are the I2 and IG, and the output current is I2 plus IG. From point B, that is the I1 is flowing through this. Within that, IG is the outgoing current, so the remaining current will pass through the R2, and those remaining current will be equals to I1 minus IG. So at point C, the situation would be something like this. It is I1 minus of IG plus I2 plus IG. This plus IG and minus IG will gone, and the term that remain is I1 plus I2, which is equals to I, and it will be coming back. Is it clear? Is it? Any doubts? Anything? No? So this is just the circuit diagram, and what do we call? We call it that if potential at B and potential at D is equal, if VB is equals to VT, if these two are the equal, then IG would be equals to 0. Why and how I could say like this? It's an, look at here, it's I is equals to delta V by R. If I write delta V, it's a, let's suppose it's a V1 minus V2 divided by resistance. If this V1 and V2 are equal, if V1 equals to V2, if these potentials are equal or they are the equipotentials, then current through that branch would be a 0. And if current through that branch would be a 0, circuit would be very easy for me. Why? Because if this has been removed, if this section has been removed, now it is very easy because R1 and R2 are in series. This R3 and R4 are in series, and the equivalent of R1 R2 is in parallel with the equivalent of R3 and R4, and things can be done very easily. I hope these things are clear. So this is the principle on which we are working for the balanced Western bridge. Now let's just check it out that how this can be derived. Yes, let's have a look. Suppose initially we are applying a loop to the ABDA. It's an ABDA. We are starting from the A, moving to B, D, A. So let's have a look. It's an from A to B, it's an minus of I1 R1, plus from D to A, it's a plus I2 R3, and that would be equals to 0. So if I solve this, it's an I1 R1 is equals to I2 R3. This is relation number 1. Please note it down. Please note it down, and we are going to use this relation. This is I1 R1 is equals to I2 R3. Now let's apply second KVL, second loop to the KVL. It's a B, C, D, B. Yes, it's a minus of I1 R2 plus from here to here it's a plus I2 R4, and that would be equals to 0. So if this is equals to 0, I can write like this. It's an I1 R2 is equals to I2 R4. So this is my second relation. We have a two relations. Let's just write it down. It's an I1 R1 is equals to I2 R3, and I1 R2 is equals to I2 R4. If this is the situation, and if I take a ratio of this two, then I could have R1 by R2 is equals to R3 by R4. Yes, that we used to have a relation like P by Q should be is equals to R by S. Look at this. It is the same ratio. Yes, it's an R1 by R2 is to R1 by R2 is to R3 by R4 in this situation. So if this is the case, if this is the case that if R1 by R2 is equals to R3 by R4, then Ig will be equals to 0. And why Ig will be equals to 0? Because VB and VB are on the same potential. So this is how we can derive balanced Western bridge, or the conditions for the balanced Western bridge, that if the ratios of this resistors are equal, P by Q should be equals to R by S. If this is the situation, then we can write like that Ig would be equals to 0, and if Ig would be equals to 0, potentials on this two terminals would be the same. Is it clear? Great. Have a look. Question. It's an Western bridge can be used to compare to unknown resistance. Yes, could it be? To measure small strains produced in the hard metals. Even it could be there. As the working principle of meter bridge. Yes, at this point of time we are not knowing the meter bridge, but yes, it can be used. So this all of the above are the correct. Yes, so this is applications. These are the applications of Western bridge. You can take a note of this. Yes, these are the applications of Western bridge. Let's look at the second question. Western bridge is most sensitive when the arm ratio is, yes, it is equal to 1. Something like this. It's a P by Q that should be equals to R by S, and this is more sensitive. This is the most sensitive when P by Q or R by S is equals to 1. Is it clear? Is it? Great. So have your pen and paper and let's just try it with me. What question is saying? That if R1 and R3 is the 10, R2 is 100, and R4 and R5, this are the 30 ohm, the equivalent resistance between A and B. That is what I require. So what I need to do is that this is the point A, this is the point B, and I cannot see it clearly that whether these are connected in series or whether these are connected in parallel. So in this kind of situations, what I need to do is I need to simply give them a name and try to redesign the circuit in a more easier way so that I can identify that which are they which are connected in series, which are connected in parallel. So let's begin then. This is point A, even this is point A. This is point B, even this must be point B. From here it's an A to this point, but our resistance is there, so let's write it down. It's a C. Let's suppose even this is C. This is B. This would be some new. It's a D, D. Yes. So what I need to do is it's an A at this end, B at this end, and let's say D at this end, C at this end. So if this is the situation, I need to write it's an from A to D. It's an R4. This is R4. Cut it down. Next, from A to C, it's an R1. Cut it down. Next, from C to B, it's an R5. Next, from B to D, it's an R3. Next, what happened? It's an A to B. This is A to B, which is equivalent to R2. Okay. So I required the resistance between A to B. Yes. So if you observe this very carefully, that R4 is of 30, R5 is of 30, then R1 and R3, this is 10, even this is 10, and R2 it is of 100. Yes. So if you observe this carefully, this three networks, that is the upper end, the middle one, and the lower end networks, are in parallel with each other, and this 30 and this 10 are in series with each other. So that means they can be related as this is 40 ohm, this 30 plus this 10, again this 30 plus this 10 would be a 40, and this is of 100. So what you need to do, you need to simply solve this. It's a 1 by R1 plus 1 by R2 plus 1 by R3. This is 1 by 40 plus 1 by 40 plus 1 by 100, and get your things done. I hope these things are clear. Is it? So can you do it on your own? Will you be? Great. Ready for the next question? Let's have a look what the question is saying. It says that the equivalent resistance between A and B. Okay, so you have a situation similar to this. It's an A to B. Yes, so this is the situation. How should you deal with it? This could be P, this could be Q, this could be R, this could be S. Let's take a ratio of this. It's a P by Q, which can be written as 5 by 15, which is 1 by 3, and R by S, which is 10 by 30, could be written as 1 by 3. So if this 2 has gone, this would be definitely removed. Yes, and if this has been removed, then what I can have is that A to B, this is A, this is B, this is 5 ohm, this is 10 ohm, which is 15 ohm, this is 15 ohm, this is 30 ohm, which is 45 ohm. So R can be written as 15 multiplied by 45 divided by 15 plus 30, which is equivalent to 45. So this 2 has gone, this 2 has gone, and I can have that it would be equals to 15 into 45. Sorry, I made a mistake. This is 15 into 45 divided by 15 plus 45, it's a 60. So this is 15 4s are 60 and 45 by 4, which is 11.25 ohm. This would be the clear. Yes, yes, great. Now the question is, in the above problem, the equivalent resistance between C and D. Okay, so now they want that what should be the equivalent resistance between C and D. How should I do it? Let's suppose they want something like this, that if my battery has been connected over here, if it is the battery that has been connected over here, what should be the equivalent resistance? So what is the difference? So in this question, in the same question, this is the case of balanced Western bridge. Even we have discussed this in the series and parallel combination. Here we are going to discuss it one more time, that suppose you want to find out an equivalent resistance on a diagonal, that is, in this case we have been find it out the resistance between A and B. Yes, and the fifth resistance has been connected on the opposite diagonal. It could be the case of Western bridge, but you have connected your battery, or you have connected your supply at the same diagonal where fifth resistance is there. I'm talking about this resistance. Yes, then it could not be the case of the Western bridge. So now in this case, when I'm talking about the C and D, it is just the case of three parallel branches. So this is 5 ohm, this is 15 ohm, it's a 5 plus 15 20, and this is 10 plus 30 40. So situation is, let's say this is C, this is D, it's a 5 and 15, it's a 20, and it's a 40. It's a 5 plus 15, this is of 20, one more of 20, and one more of 40. This is C, this is T. So what you need to do is, it's a 1 by R, could be written as 1 by 20 plus 1 by 20 plus 1 by 40. So this is equals to 2 by 20, that is 1 by 10 plus 1 by 40, which could be written as 4 by 40 plus 1 by 40, which is 5 by 40. So R equivalent can be written as 40 by 5, which should be is equals to 8 ohm. That's it. You did it. Great job. What was your answer? Do you have a same answer? Do you? Yes. Great. Ready for the next question? Yes. Let's have a look then. What does it say? It says effective resistance between A and B in the given network. Take your time of 10 seconds and try to do it. Do it. Yes, can you? Can you? Let me help you. This is A and this is B. Yes, if I am moving on this path, a resistance is there, so I need to give a new name. It's a C. If I am moving on this path, again resistance is there, give it a name as a D. Where do I need to find out? It's a to B. So let's write it down, A at one of the corner, B at another end. And what else is required? It's a C and a D. These two are required. So if I write, it's an from A to D, have one of the resistor. This is from A to D, value would be the R. one more resistance from A to C. Again it is of R, cut it down. Next from C to B, one of the resistance, this is R, and from D to C it is R, this is gone. Yes, and from D to C, yes, this is R, even this has been removed, and your supply has been connected over this path. So a fifth resistor is connected on the opposite diagonal than the battery. So if it is the case, this could be the Western bridge, or this could be the balanced Western bridge. So what you are supposed to do is, this is P, this is Q, this is R, this is S. So if I take a ratio of P by Q is to R by S, it is same, it's an R by R is to 1, R by R is to 1. So this is the resistance where no current is flowing, and if no current is flowing, it we do not need to require it. So this two are in series, which could be drawn at like this, it's a 2R, and even it is the case of 2R. So let's say this is A, this is B. So R equivalent can be written as 2R into 2R divided by 2R plus 2R. This is equals to 4R. So this is R ohm. This is what we required. It's an R equivalent which is of R ohm. I hope those things are clear. Is it clear? Is it? Any doubts on this? Anything? Anything? No? Great. Well done. So I hope Western breeze would be the clear. Yes, and you can solve the questions of in the cases of balanced Western bridge. Yes. Now let's look at the practical application of Western bridge, and that is a meter bridge. In meter bridge we are going to use the same concept that we were using in the Western bridge, that if the ratio of P by Q is to R by S is the same, then what we can do, we can just eliminate the fifth resistor because no current is flowing through this, and find out the resistance. So let's look at this. This is the practical setup. This is the practical setup of meter bridge. The situation is here, one of the resistance would be the X, another resistance would be the R, and this is a wire from A to C. This is a wire from A to C. This wire is meter wire. Yes, on a standard notifications, this wire should be of length of 100 centimeter or 1 meter. Yes, and what I'm supposed to do is, I have connected one jockey over here. The task of jockey is to change the location. Yes, because it is having this jockey constructions, and if this jockey has been connected over one of the point, that means it has divided the total resistance of the wire into two segments. Yes, one length could be considered. I know that R is directly proportional to the L. So when this is the situation, when R is directly proportional to the L, so one of the length will become Lx and another length will become 100 minus Lx. So as length are different, the resistance would be this different, and so on. We are going to calculate the remaining task. Basically this is being used to find out the unknown resistance. Yes, so let's have a look then. So this is what we have discussed. This is 1 meter wire, resistance X, resistance R. Yes, so X, if I take a ratio that, suppose if X by R is to resistance from this wire from this point A to this point D, it's a resistance of wire AD to the this is resistance of wire D to C. This is the situation. Yes, what I have done is that I have using trial and error, I have find out the null deflection, and at this point I have find out the null deflection. While I say null deflection, that means Ig should be equals to 0, and Ig equals to 0. This could be the case only one time, when this is the case of balanced Western bridge. So I have did the same thing. It's an X by resistance of wire AD, that should be is equals to R divided by resistance of wire DC. And if I take a ratio of this could be the situation. Now I'm defining one more term, that at this point of time I'm defining by sigma. It is the resistance per unit length. Yes, and that could be written as, so resistance could be written as R is equals to sigma into L. So resistance of wire AD could be written as, it's a sigma into Lx, and resistance of wire DC could be written as, this is Lr is equals to 100 minus Lx. So this is sigma into 100 minus Lx. I hope these things are clear. So this could be written as X by R. Sigma has been gone, and this could be Lx divided by 100 minus Lx. From this you can find out the X. It's an R into bracket Lx upon 100 minus Lx. Now I know the value of the R, we know the value of the Lx, and if we know this too, we can have the data of X. This is what we require to find out the unknown resistance. That is why we are using the meter bridge. Is it clear? Is it? Great. So we will go through the numericals, and as soon as we go through it, there would be a more clearer idea would be there. So let's have a look. That in a meter bridge experiment, when the resistance in the gaps are interchanged, the balance point did not shift at all. The ratio of the resistance must be, so this is the situation, that initially let's suppose this is the P, this is the Q, and this is the situation, that this is the galvanometer and this is the jockey. Yes. Now let's suppose this is the resistance R1, this is the resistance R2, suppose. Yes, that means I'm talking that resistance of this point, resistance of AD is R1 and resistance of DC is R2. Now let's suppose that this is Q, this is P, and this is the jockey. Again, this is A, this is D, this is D, this is C. This would be the R1, this would be the R2. So in the previous case, in the first case, the situation was, it's a P by R1, that should be is equals to Q by R2. Now in this case, the situation is Q by R1, that should be is equals to P by R2. Now if this is the null point, even in this case null point remains the same. This could be situation when P and Q will be equals to, P and Q will be same, and the ratio of them must be an unity. I hope those things are clear. Is it clear? Any difficulties in this? Yes, we are going to see more questions of the meter bridge, but before we go through those questions, first we are going to discuss about the potentiometer and how does it work and all its applications of the potentiometer, and at last we are going to discuss the applications and the numericals based on the meter bridge, potentiometer and Western bridge. Is it clear? Is it? So let's have a look then. So let's look at the principle of potentiometer, and we are currently using the individual cell method. So Let's have a look what potentiometer is and all the things about the potentiometer. That this is the circuit diagram of the potentiometer, and what we understood is that this is the A to B point, and it has been connected with certain battery E, and a switch has been connected, and this is what we call as a master circuit. Yes, the point P has been chosen, and the potential or the potential difference between point A and P is represented as VAP. So this is the potential difference between any 2 points of the potentiometer wire. Carrying steady current is directly proportional to the length of the wire between these 2 points. Now, what I know according to the Ohm's law, V is equals to I into R. And in previous slides only we have defined that sigma should be R by L. So for RAP, it's a resistance between point A to point P is R can be replaced as sigma into L. R can be replaced as sigma into L. So that can be written as I into sigma into L, and thus VAP, it's a voltage between point A and P, can be represented as directly proportional to the length. So as length is increasing, the potential is decreasing, and same for the length is decreasing. Is it clear? Is it? Yes. So we define potential gradient. Potential gradient is defined as the potential drop per unit length. We can say this is VAP by L, and that can be represented by certain constant K, because I know VAP is directly proportional to the K, and this K, it's a potential gradient of the wire that can be written as V by L. It's a unit voltage per length. This is voltage per length that we call as a voltage gradient. Please do remember, when word gradient is there, when word gradient is there, this represents that a certain quantity is divided by length. Yes, in class 11 you might have come from the temperature gradient. Yes, it's a temperature divided by length. Now it's a potential gradient, it's a potential divided by length. So when gradient is there, when gradient is there, it means it is divided by length. Now let's look at the use of potentiometer. First, to measure the EMF of a cell. Second, to compare the EMF of two cells. And the third, and very important, it's a to determine the internal resistance of a cell. So let's look at each application one by one, that how we are going to use it. So let's first compare EMF between two cells. That this is the master circuit. This circuit is the master circuit, and here two cells have been connected. One is the E1, another is the E2, and we have provided with the two kits K1 and K2, so that each cell can be individually connected, or each cell can be removed. So now if you understand the situation carefully, that suppose this is the galvanometer and this is the master cell. When this key is switch on, or this key is closed, then current is passing through this path. From the total current I can be moving from here to here, from here to here, from here and onwards. This is the rheostat. I hope you understand what rheostat is. It's a variable resistor. So what you are supposed to do is you are going to connect any one of the cell to the circuit, and with trial error situation you are going to find it out a location where null deflection is find it out. It's a null deflection. That means current through IG should be 0. It's a current through galvanometer should be 0, or IG should be 0. So what we are supposed to do is that as no current flows through the cell even at this point, the potential difference across the AP from here A to this location here, it's a potential difference across AP is the EMF of the cell even. Yes, we know from the concept of Western breeze that when current is not flowing through the circuit, if they are the equipotential points, so if you are connected, if you have connected your jockey at point P, so A to P, this is the length where no current is flowing, or my galvanometer is showing a null deflection. That means a potential of this, it's a potential of E1, and potential from A to P must be same. If this is the case, what I can write, it's a E1 that can be written as VAP. This is the point P, and that can be represented as K into L1. So I can have that E1 is equals to K into L1. Yes, as no current flows through the cell E1 at this point, the potential difference across the AP is the EMF of the cell E1 that we have discussed in the last slide as well. I hope these things are clear. Is it? Now let's have a look to the next question, next situation. Now what we are supposed to do is that I have opened this and I have closed this. That means now whatever the effect will be, that will be of E2 cell. So again I do the same task. This has been disconnected and this has been connected, and with trial and error I am searching out for the null point. And let's suppose at point P dash, I am having that null point. So potential from A to P, dash is same, that should be equals to E2. So I have a relation that is of E1 equals to KL1, and then I am having the relation that E2 should be is equals to this, E2 should be equals to KL2. I hope these things are clear. Yes, so these are the relation, E1 is equals to KL1 and E2 is equals to KL2. These two relations are there. And now if I take a ratio of this, it's an E1 by E2, that should be is equals to KL1 by KL2, and this KK could be gone, and this is E1 by E2, that is equals to L1 by L2. So what I can understood is this is E, which is directly proportional to the length L, and this E is the EMF of a cell. This is the beauty of potentiometer, that it can measure EMF, that is electromotive force of a cell. Voltmeter is also there, but it cannot measure EMF. It always measure terminal voltage or potential difference. This is the capability of a potentiometer, that it can measure EMF of a cell. Yes, so that's why if we are having a potentiometer as well as we are having the voltmeter, we are going to prefer the potentiometer. Why? Because it can measure EMF of a cell, or rather you can say that it can measure a potential difference when no current is flowing. That means the I into R drop would be equals to 0. Yes, so let's look at certain questions. Potentiometer is an ideal instrument because no current is drawn from the source of unknown EMF. Current is drawn from the source of unknown EMF. It is given deflection even at the null point, and it has variable potential gradient. Yes, this is correct, because no current is drawn from the source of unknown EMF, and if no current is drawn, that means I into R would be equals to 0. Yes, and that's why potential drop is not being wasted. Yes, so this can measure EMF. Second, if the value of the potential gradient on potentiometer wire is decreased, potential gradient, yes, then the new null point will be obtained at, yes, potential gradient, let's say V by L, and assume that this is K. If the value of the potential gradient on the potential wire It's if this is going to be lesser, if this is going to be lesser, then what I can understood is that V is the constant because V has been supplied from the source battery, or we can say it's a master battery. So it's a K into L that could be considered as a constant. So K is inversely proportional to the 1 by L. If this is decreasing, then this must be increasing. So you are going to have a null point at higher lengths. Is it clear? Same way, if K is increasing, then L should decreasing. That means you are going to have a null point at a shorter length. Yes, got it? Great. Let's look at this question. The temperature coefficient of resistance and resistivity of potentiometer wire must be. Yes, this is the information kind of question, but you must remember this, that temperature coefficient of resistance and resistivity of potentiometer wire should be, temperature coefficient of resistance should be low, while the temperature coefficient of resistivity of a potentiometer wire should be high. Yes, well, let's have a next question. It's a sensitivity of potentiometer. Yes, the sensitivity increases with increases of length of the wire. We can have this V by L, that is directly proportional to the K. So V is directly proportional to the L. Yes, as length is increasing, its potential is increasing, and its sensitivity of potentiometer is also increasing. Is it clear? Is it? Great. Now let's look at the second applications of the potentiometer wire to find internal resistance of a cell. This is very important because we know that what EMF would be of what would be the EMF of the second cell. Now we are working to find out the internal resistance of a cell. Let's have a look. This is our master circuit. This is the master cell, and this is what we can say it's a secondary. It's a secondary circuit, and the supply has been connected, and we have one cell over here. This is the internal resistance. This is why we are working for, and here one of the rheostat has been connected. Yes, this is the variable resistance R, and here one of the switch is connected. Initially what we are supposed to do is that we are going to open this circuit. It's a K1 would be the open and K is closed. So what the situation is that suppose this has been open and there would be no current. There would be no current through the secondary circuit, and I am having the jockey construction. Then I am going to find out by trial and error that where the null point can be obtained. So I am getting the null point at point P. So what I can write, it's a null point is equals to AP is equals to L1, and according to the principle of potentiometer I can have like this. It's a VAP. VAP could be written as K into L1, and as no current is flowing, this VAP would be the same as the EMF of the first cell, that is equals to E1 equals to K into L1. Are you clear up to this? Are you? Great. Now what would be the next situation? That E1 equals to KL1. This is what we have derived. Now what we are supposed to do, I'm going to close this path. That K1 is closed, and let's suppose again trying to find it out, the null point. So again doing the same thing. This has been removed, and I'm just searching out for the null point, and let's suppose I am finding the null point at AP dash. So null point P dash is obtained, and this AP dash can be written as L2. Yes, so this AP dash is equals to L2, and by principle of potentiometer it is the V which is equals to K into L2. This is the VAP dash, that should be equals to K into L2. Is it clear? Now here I have not written that VAP would be equals to certain EMF, because this could not be considered as EMF, because this is the potential difference. Why this is considered as a potential difference? Because current is flowing through the circuit. Here the current is flowing through circuit. Now if you remember the basics, when we were discussing the potential difference and the EMF, at that point of time we said that it is EMF if current is 0, and it is a potential difference if current is not equals to 0. As I have closed the switch, current must be flowing through this, and if current is flowing through this, it could not be an EMF, it must be the potential difference. Is it clear? Yes? Great. Now let's look at the relations. We have this, that is the E1 equals to K into L1, and we have this too, it's a V is equals to K into L2. Let's take a ratio of this, that is the E1 by V, that should be equals to this K has gone, and this is equals to L1 by L2. Now suppose I is the current in closed circuit formed by E1 R and all in series by Ohm's law, that I can write like this, it's E1 equals to I into bracket R plus R, and I am having this relation, that is the V is equals to IR. So let's take a ratio of this, it's an E1 by V, which is equals to R plus R by R. In the previously we have a relation of E1 by V as L1 by L2. So when this was the relation, what I am having, E1 by V is equals to L1 by L2, and that could be written as R plus R by R. So let's just try to get it solved. So from this I can have, it's an R plus R by R, which is equals to L1 by L2. R by R, it's a 1 plus R by R, that should be equals to L1 by L2. I am working for it. So this is R by R, which is equals to L1 by L2 minus 1, and this is the internal resistance of a cell. Please do remember this. R is equals to R into bracket L1 minus L2 by L2. Now in this situation, L1 is the length of null point when no current is flowing, and L2, it is the length of null point when current is flowing through circuit. Is it clear? Is it? So please take a note of this. Please note down the relation of internal resistance, as well as please note down what is L1 and what is L2. Take a 10 seconds of time and get it done. Did you? Have you completed it? Have you? Great. Let's look at the basic difference between potentiometer and voltmeter. This is very important from your board exam point of view, as well as concepts. To make the concepts clear, this is required. So let's have a look. What is potentiometer? A potentiometer is one which measures terminal potential difference as well as EMF of a cell. Yes, This measures only the terminal potential difference. Potentiometer, this accuracy can be increased by increasing the length of the wire. Yes, that we have discussed, or we were discussing in the MCQs. Beyond certain extent, accuracy of voltmeter cannot be increased. Here, a small potential difference can be measured accurately. This voltmeter has a very high but finite resistance, hence cannot measure the very small voltage. This does not provide direct reading, this provides a direct reading. And this is not portable because it contains a meter bridge, it contains a potentiometer wire and all that stuff. This is not portable, but this is portable, yes. So both have its own pros and cons. But what we are considering is that if I required a potentiometer, if I required a EMF of a cell, I must go with the potentiometer because voltmeter cannot provide me the EMF. It can always provide me the voltage or the potential difference between two terminals, but it is unable to provide me the EMF. So when I require EMF, I must go with the potentiometer. And even the accuracy of potentiometer is higher as when we compare it with the voltmeter. So is it clear? Is it? Shall we move to the questions? Shall we? Let's have a look then. The quantity that cannot be measured by potentiometer. Resistance, yes, this can be measured. EMF, that we know. Current in the wire, yes. Inductance cannot be calculated. Yes. Next question, let's have a look. These are the questions we are working for. Yes. So do one thing, have your pen, have your paper, and do it with me. Yes, we are going to check the answers at the end of the question. What is saying in the meter bridge? 20 ohm is connected in left gap and unknown resistance is connected in the right gap. So situation is something like this, that this is the left gap where we all have placed 20 ohm. Unknown resistance, let's say X, is connected in the right gap and balancing length is found as 40 centimeter. Okay, so this is the galvanometer and let's suppose from here this is of 40 centimeter, so this is by default a 60 centimeter because we discussed that a meter bridge is having a 1 meter of wire and it is having the uniform resistance. Now without changing the resistance in the right gap, 10 ohm is kept in the left gap. Now balancing length becomes okay. So what you need to do is first find it out what would be the value of X. So how could I do this? That this is the null point. The null point could be there if I am having 20 by 40. Yes, this is the length, but as I know that R is directly proportional to the length. Yes, I can use it. It's a 20 by 40, that could be equals to X by 60. Yes, this is 22 and this is 2 3s. So X, that is the unknown resistance, is having a value of 30 ohm. This unknown resistance is having a value of 30 ohm. Now what they are saying, without changing the resistance in the right gap, that means this 30 ohm will be kept as it is. 10 ohm is kept in the left gap, so the situation should be, this is the 10 ohm, this was the X which you have find it out is of 30 ohm, and this is the jockey and you are searching for it. This is the, let's suppose this is X, then this should be 100 minus X. So again it is having null point, or current through this would be a 0 if 10 by x is equals to 30 divided by 100 minus of x. Yes, so let's just try to get it done. It's a 10 into 100, which is 1000, minus of 10x, that should be is equals to 30x. So this is equals to 1000 is equals to 10x plus 30x, which should be an 40x. This is gone, and x should be equals to 100 by 4, which is 25 centimeter. So my null point or the new balancing length will be at 25 centimeter, or I can say my null point has been shifted by 15 centimeter, because initially it was 40 and now it is 25. So it has been shifted by 15 centimeter in this direction. What was your answer? Can you get it done? Can you? Great. Ready for the next question? Let's have a look. So when a case of meter bridge or when case of western bridge is there, first thing you need to understood is that you must have a rough sketch of meter bridge or western bridge. Then and then you will be able to solve this. Otherwise you cannot remember just the formulas and get it done. This is simply impossible. Yes, but with the help of diagram and with the help of little sense of voltage and EMF, we are able to do it. So let's have this question. The resistance in the left and right gaps of a balance meter bridge are R1 and R2, and the balance point is 40 centimeter from the left. Okay, so the situation is, this is R1, this is R2, and balance point it is at 40. So galvanometer, and this is, let's say, 40. If this is 40, that means this must be the 60. Now then they are saying if 10 ohm resistance is connected in series with R1, then the balance point is at 60 centimeter, the value of R1 and R2. Okay, great. So let's do it this task only. So R1 divided by 40 should be equals to R2 divided by 60. So it's a 22 it's a 23 so this has gone, and what I can have, it's an R1 is to R2 can be written as 2 is to 3. If required, I can do this. Yes. Now what they are saying, if 10 ohm resistance is connected in series with the R1, so the situation is, this is R1, this is 10, and this is R2, and now new balance point, the new balance point is at 60 centimeter. So it is somewhere here. This is 60, this would be the 40. So what I need to do, it is R1 plus 10 divided by 60, that should be is equals to R2 divided by 40. This has gone, and this is 2 2s are, this is 3 2s are, it's a 2 and 3. So this is 2R1 plus 20, that should be is equals to 3R2. Yes, even I am having the relation, it is R1 by R2, R1 by R2, that should be 2 by 3. So what I can have, it's an, let's replace the value of R1, that is the R1 could be equals to 2 by 3 R2. So that should be is equals to 2 into 2 by 3 of R2 plus 20, that should be is equals to 3 R2. So this is 2 2s are 4 by 3 R2 plus 20, that should be is equals to 3 R2. So this is of 3 R2 minus of 4 by 3 R2 should be equals to 20. This is 3 3s are 9, 9 minus 4, which is 5 by 3 R2, which is equals to 20. So this is 5 4 and R2 would be equals to 12 ohm. R2 would be equals to 12 ohm. When R2 is equals to 12 ohm, R1 could be written as 2 by 3 multiplied by 12. So this is 3 4 and this is R1, which could be written as 8 ohm. So R1 8 ohm, R2 12 ohm. Yes, you did it. Great job. I hope these things are clear. Is it? Is it clear? So will you be able to solve this? Will you? Great. Let's look at the next question. What does it says? Make it fast. It says a battery of EMF 2.2 volt and internal resistance 1.2 ohm is connected to a potentiometer wire of length 10 meter and a resistance of 9.8 ohm. Find the potential drop per centimeter of length of the wire. Okay, so let's have a sketch of it. A battery of EMF 2.2 volt and internal resistance 1.2 ohm is connected to a potentiometer wire of length, this is the potentiometer wire, of length 10 meter and resistance is 9.8 ohm. I need to find out, this is, let's say that this is point A, this is point B, this is the length of a potentiometer wire. I need to find out the potential drop per centimeter of length of the wire. So what I need to do is, I want potential drop per centimeter of length of the wire. So what initially I need to find out the current that is flowing through this. So current can be measured, it's a V divided by internal resistance plus resistance of this, it's a R plus R external. The V, it's a 2.2 divided by this is 9.8 plus this is 1.2 ohm, and that can be measured as 2.2 divided by 9.8.2, it's a 10 plus 1, it's an 11. So this is 2.2 divided by 11 and could be written as 1 by 5 ampere, or I can have it's a point of 2 ampere. So this is the current that would be passing through this. Now potential drop per centimeter, what I can have, it's a V is equals to I into R. The current is 1 by 5, the current is 1 by 5 ampere and the resistance is 9.8. Now I don't require V, I require V by L. So this is potential drop per unit length, this is equals to I into R by L. This is equals to 1 by 5 multiplied by 9.8 divided by 10. This is V by L. I hope these things are clear. Is it? Yes, this is 9.8 divided by 50 volt per meter. Even you required for centimeter, you required this for centimeter. So what you need to do is, this is per meter and you need to convert this to per centimeter. I hope you can do this. Can you? Will you be able to solve this? Are you sure? Great. So shall we move to the next question? Shall we? Okay, let's have a look what it is saying. It says that a 10 meter long wire of resistance 15 ohm is connected in series with a battery of EMF 2 volt. Yes, it is not having any internal resistance and a resistance of 5 ohm. The potential gradient along the wire, okay, EMF is there which is of 2 volt and a resistance of 5 ohm has been connected with a 10 meter long wire. This is 10 meter long wire having resistance of 15 ohm. What do you need to find out? You need to find out the potential gradient. It is almost same question. Do it with me. This is current. Find out the current which is equals to I, that would be equals to V divided by 15 plus 5. This is of 2 volt. 15 plus 5, it's a 20. This is 1/10 of ampere. Now let's just calculate V is equals to I into R. This is of 1/10, and I'm talking about the potential gradient of this point from A to B. This is 1/10 into 15. This is equals to 5 3s divided by 5 2s. So this should be is equals to 3/2. This is 3/2, but this is just the potential drop. What I am searching for is the potential gradient, so that should be V by L. That should be equals to IR by L. So this is 3/2 into 1 by L, that is of 10. It's 3/20, and rest of the thing you must do it. Is it clear? Is it? Will you be able to solve this kind of question? Will you? Great. Let's look at this question. What is it? In a potentiometer experiment, when two cells are joined in series to support each other and then joined to oppose each other, balancing points are obtained at 6 meters and 2 meters respectively. The ratio of their EMFs. Yes, very good question. Beautifully asked. That when it says that when two resistors are connected such as they are going to support each other, if you remember the combinations of the cell, this could be written as E1 plus E2, and in one of the situation they are going to oppose each other. That let's assume this is E1, this is E2, and I am assuming that E1 is greater than E2, so this is E1 minus E2. Yes. Okay. Now from the potentiometer we know that E is directly proportional to the L. E is directly proportional to the L. This is the principle of potentiometer. So if I write this, what I can have, it's an E1 plus E2, that is equals to let's say 6 meter, and E1 minus E2, that is equals to 2 meter. So let's take a ratio of this. This is 2 3s and E1 plus E2, that should be is equals to 3E1 minus of 3E2. So this is E1 minus of 3E1, or let's say this is 4E2, that should be is equals to 2E1. So E1 by E2 could be written as 4/2, which should be equals to 2:1. Yes, this is the correct answer. What was yours? Is it the same? Is it? This is the answer. Is it same? Yes. So will you able to solve this kind of questions? Is it possible to get it done? Are you sure? Well done. You are doing a good job. Let's working for the next question. Do it quickly. What the question is all about? It says that in an experiment to determine the internal resistance, okay, I'm going to do this, internal resistance of a cell with potentiometer, the balancing length is 260 centimeter, and now when a resistance of 3 ohm is joined in parallel with the cell, the balancing length is 150 centimeter, the internal resistance of the cell. So what does it say? It says that when at initial level balancing length is 260 centimeter, that means they are indirectly indicating that when no current has been passed through the secondary circuit, your balancing point or the null point can be obtained at 260 centimeter. And when a resistance of 3 ohm is joined in parallel with the cell, when this resistance has been connected in parallel with the cell, the balancing length is at 150 centimeter. So this is the situation. If I try to solve it, it's an R which is equals to L1 by L2 minus of L2 multiplied by R. and the resistance is of 3 ohm. So this is equals to 260 minus 150, which should be 110, divided by L2, it's 150 multiplied by 3. So this has gone, and this is 3 by 5. So this is 11 by 5, which is equals to 2.2 ohm. Is it clear? Is it clear? Will you be able to solve this? Will you be? Great. Let's look at this question. The resistance of potentiometer wire is 0.9 ohm per meter. So this is not only the resistance, this is R by L. It's a 0.9 ohm per meter. Now the potential gradient, that is the V by L, is 0.0081 volt per meter. Current is required. So what I can have, it's a V is equals to IR. Let's divide it by L. So this V by L, which is equals to 0.0081, that should be is equals to I, multiplied by R by L. This is 0.9. From this you can have this I, and solve the equation and get it done. This is 0.9 ampere. Clear? Next question. Let's just look at this question very quickly. When two resistors P and Q are kept in the left and right gaps of a meter bridge, the null point is obtained at 60 centimeter. If P is shunted, what does it mean? When we have been asked to keep it in a shunt, that means they want that we want to connect it in parallel. If P is shunted by a resistance equal to half of its value, then the shift in the null point is, okay, very good question. What is saying, it's a P, let's say this is Q, and the null point is obtained at 60 centimeter. So if this is at 60, this must be at 40. So what do we require? It's a P by 60, that should be equals to Q by 40, and this is 22, this is 23. So this is P is equals to 3 by 2 of the Q. Now what we are going to do, that if P is shunted by a resistance equal to half of its value, so the situation is that this is, let's say this is X, and this has been parallelly connected by X by 2. This was Q, this was the Q, and now let's suppose new balancing length is to be required. So what I can do is, this is X, this is X by 2. So first let's find out RP dash, the new resistance of P. It is they are connected in parallel, it is an X into X by 2 divided by X plus X by 2, which should be an 3X by 2. So this is X square by 3X, which could be written as X by 3. So if initially it was resistance P, now it's a P by 3. So now it's a P by 3 into, let's suppose this length is Y, then this length must be 100 minus Y. So this is P by 3Y, should be written as Q by 100 minus of Y. Now I am having the relation, that is of P is equals to 3 by 2 of Q. It's a 3 by 2 of Q into 3Y. That should be is equals to Q by 100 minus of Y. This 3 has gone, this 3 has gone, and that could be written as this Q even is gone. So this is 100 minus of y should be equals to 2y. So 100 could be equals to 3y, and y could be equals to 100 by 3, which is equals to approximately 33.33 centimeter. So initially at 60, now it is at 33. 33 would be somewhere here. So it has been shifted in this direction. It has been shifted in this direction. And how much it has been shifted? It's an 60 minus 33. It's an 26.7 centimeter to the left. I hope this is clear. Is it clear? Are you sure? Can you do this kind of question? Can you? Great. Let's look at the next question. Just have your patience. We are on completion of the session. Yes. So 2 more questions and it will be over. So please have a focus on this and get it done as soon as possible. The resistance in the left and right gap of a balance meter breach are R1 and R2. The balance point is at 50 centimeter. If a resistance of 24 ohm is connected in parallel to R2, then the balance point shifts by 20 centimeter. Look at this. It says it is being shifted. This is not the new position of null point. This is where we are making a mistake. So what I need to do is that this is first, this is second, let's say this is R1, this is R2, and the balance point is at 50 centimeter. So this is 50, even this is 50. So if I solve this, it's an R1 by 50, that should be is equals to R2 by 50, and R1 must be equals to R2. Yes, this 2 must be the same. Now if a resistance of 24 ohm is connected in parallel to R2, so let's say this is X, because we know that now both would be having a value of same, and this has been connected with 24 ohm. Then balance point shifts by 20 centimeter. That means initially it was 50 centimeter. Initially it was 50 centimeter, and now it has been shifted. Now it has been shifted by 20 centimeter towards the right. That means initially it is at 50, now it is at 70. It is somewhere here. This is 70 and this is 30. Is it clear? Is it? Yes. So if I solve this, it's an X divided by 70 is equals to, this is X, this is 24. These two are connected in parallel. So can be written as X into 24 divide by 24 plus X divide by 30 centimeter. I hope this is clear. Is it? So this XX gone. This is 24. This is 6 4s are. This is 6 5s are. So this has been gone, and 5 14s are 70. So I am left with 24 plus X, and that should be equals to 14 into 4, which is a 56. So X can be written as it's a 56 minus of 24. This is 6 minus 4 2, 5 minus 2 32. This is X, the value of an resistance. It's a 32 ohm. What was your answer? What was it? Is it same? Does it? Great. You did great job. Well done. Keep it up, and let's focus on the next question. And this is the last question of this class. So let's do it very quickly. What does it say? It says that in meter bridge, when P is kept in the left gap and Q is kept in the right gap, and that at that time at balancing length is of 40 centimeter. Now if Q is shunted by 10 ohm, the balancing point shifts by 10 centimeter. You need to find out the resistance of Q. So in this situation, this is P, this is Q, and balancing length is at 40 centimeter. This is the null point at 40. This must be at 60. Now it's a P by 40, that could be written as Q by 60, and from this I can have that it's a P equals P by 2 equals to Q by 3. So this is P equals to 2 by 3 of Q. Now Q has been shunted, that means one of the parallel resistance has been connected with the Q by 10 ohm, and the balance point shifts by 10 centimeter. So the situation is that this is P, this is Q, this is 10 ohm, and now balance point has been shifted. So balance point has been shifted by 10 centimeter. So now it is at this 50 centimeter. Initially it was at 40 and now it has been at 50 centimeter. So I need to find out the resistance Q. How could I do it? It's P by 50. That should be is equals to Q into 10 divided by Q plus 10 multiplied by 50. This has gone. Yes. So this is P is equals to 10 into Q divided by Q plus 10. Now I am having the relation which is P is equals to 2 by 3Q. So I can write like this, it's a 2 by 3Q which is equals to 10Q divided by Q plus 10. And this Q and this Q has gone. This is 2 5s are 10. So this could be written as Q plus 10 should be equals to 5 3s are 15, and this Q is equals to 15 minus 10 which is equals to 5. Yes. What was your answer? Is it same? Is it? Great, you did it. Great job, well done. So let's wind it up the session over here. Yes, this is all about the Western bridge, meter bridge and potentiometer. Yes, if you observe the previous year asked questions of each examination, that means I'm talking about the NEET as well as JEE, you will find the questions based on potentiometer, meter bridge and Western bridge over there. Yes, in generally Western bridge has been asked as an applications of the meter bridge or potentiometer, but they are going to be asked, that is for sure. So please practice as many questions as possible. Yes, this will save us. Yes, thank you, have a good day, take care, bye bye.